Hello everyone, I welcome you to the day 27 of the training. Today we are going to discuss about block RAM, and as we are approaching to the end of the training, I would like to introduce some of the interview questions, most asked interview questions in the entire job requirements, and also I would like to give you some tips and tricks in the interview preparations, also in the interview room, how to be so professional and how to make a portfolio among these projects and all. If you are a fresher and if you are a beginner and also you have some experience with projects, and if you have some good portfolio and how to get some good opportunities out there, and how to learn yourself and how to prepare for any interview that you are acquiring now, all these things will be discussed in the coming sessions. And how to build a resume as well, I want to give that resume building course training as well. So with that being said, let us go to the today's agenda, that is block ram and also the interview questions. So with that being said, let us go to the today's agenda, that is block ram, brief and functionality of it, what is the block ram, why it is more important here in this scenarios in the FPGA development, and where it is located in the group of cells, what is the major functionality, and why do we take block RAM always as an intellectual property. Usually block RAM is an intellectual property, from that you can derive the design itself in the automation of the EDA tool. So when you open Xilinx Vivado, and if you start the project with IP integrator, you can select the BRAM IP integrated, and then from the BRAM you can automate the connections and other devices as well. So you can turn your entire FPGA into one single memory device or into the block RAM. So we'll briefly understand what is block RAM and get to know the different implementations of block RAM and different types of block RAM we have in the designs. And some of the most asked interview questions, I'll try to explain them with the solutions as well in the interview questions, and how to answer them, what are the best ways to get into the interview questions. And let us go to the block RAM IP. This is a preview. We have once designed this block RAM IP in our FPGA training in the initial days, and you can refer to that video as well. But this IP integrator, when you see, this is the IP integrated diagram, and when you click on it, you can select a bunch of IPs, and in that you can select a block RAM. This is how the typical symbol of block RAM will be created, and this is a block memory generator. Now from this, if you have this entire FPGA kind of thing, that entire FPGA chip is turned into a memory block. Okay, and this is normal representation of block RAM in the general representation. So block memory generator and initial 0 value. Okay, so it is at 0. Now if you elaborate it, when you double click on it, you can see these connections, what are the inputs and outputs. So for a block RAM module, imagine you are writing a Verilog module for it, module, and you can see I will also give an example of Verilog module from the list of block RAMs that you can see from the user guide manuals, and that can be seen from this. So imagine you are writing a block RAM with this name, BRAM underscore port, some kind of representation declaration that you give in the Verilog HDL, and some inputs and outputs and semicolon. Like this you declare, right? In that way you are declaring inputs. So this is input, clock A is another input. I mean, ignore the A, that is just a representation of it. Address, address bus, clock, clock signal, data in, D in is nothing but data in, that is input, data out is output. See, since now we have designed around 2 to 3 types of memory blocks, memory designs. That also we have discussed the memory modeling in the Verilog HDL. But now today in the block RAM, if you can see, it is again a memory device, and that for that memory device you can see inputs and outputs all are same, and this is input, and this is another input, reset input, and this is enable input, and enable input is nothing but chip select, like memory. This memory is now enabled, and whatever the data read and write processes are happening, that will happen only when enable signal is high, and also clock should be high, and reset shouldn't be high, reset should be 0. Then another one is write enable. If you want to give a signal, give a command, like we have seen yesterday, like mem underscore enable, or um, some, okay, another one is write underscore enable, or mem underscore write command. Likewise for the read command you can also see. Okay, in that way input and outputs can be decided. So this is how you can see the inputs and outputs for a memory block. See, again, BRAM is nothing but random access memory, and for that you can see all the inputs like address, clock. Remember this, for any module, whatever module you have come across this far, and whatever the Verilog HDL codes you understand, and writing the test benches to the Verilog HDL codes, understand everything runs input between input and output. What is the process between that? That is a module. Simple explanations. Don't get too confused between what are we designing. No, nothing. For example, in the yesterday's session, we have to FIFO implementation. For the FIFO implementation, we have neatly explained like set of, like bunch of always blocks. For every simple task, we have set a always block. For example, always block for read and write initializations. Initialize it. Then always block for read condition. Always block for write condition. And always block, I mean, first you have to write and then you can read. And then one always block for pointers. What pointers should do? Like in the write enable command, the write pointer should increment. In the read enable signal, if read enable is 1, then read pointer should decrement. So in this way, we are writing a Verilog HDL, entire Verilog HDL code in terms of blocks. That is what you have to learn. There is no tougher science than this. The tougher science is you need to understand how you are writing procedural blocks, and also if you want to initialize the design, how will you initialize? Also, in developing Verilog HDL, there is one another type of modeling, like that is like pipeline architecturing. In the larger complex Verilog HDL modules, for example, if you are designing the larger design, entire bigger design involving all different modules, like you have 4 block RAMs, 4 or more than 4, 6 block RAMs, or you have 5 different counters, and you are involving 2 different set of clocks or 3 different set of clocks. If you are designing such a complicated design in terms of full chip, in full application oriented FPGA, for that you can see a pipeline architecture. Normally in the Intel FPGAs or Intel processor, if you take the architecture involved inside the Intel CPU, in the Intel processor, you can see a pipeline architecture. Or even in the ARM Cortex M0, you have to understand the pipeline architecture. Pipeline architecture is nothing but, okay, this set of modules are connected with this network. So that is one pipeline of architecture. They are going through that, and this can also be connected to the neighboring module. um, so for example, I'll erase everything, or let us go to the previous thing. You have more white space. Okay, now you have a bigger module, and also you have another module sitting here, and all different types of blocks connected here. And then each block B1 inside the FPGA should be designed individually, and then these can be connected, these can be interrelated with the pipeline architecture. That is another explanation in the entire FPGA training, but I would like to introduce in one of the sessions, but if not, sorry, I will be explaining separately in some other time. I'll add on as an advanced topic. So things apart, for the bigger larger memories we are using IP integrator, because we can get the memories from the vendors who have designed the memory blocks to directly use and implement inside your own project. So direct piece of hardware you can collect like this and then generate. Simple. You don't want to design from if you have remember, um, from this IP integrator we have selected block RAM and we have generated Verilog HDL wrapper. So we have generated Verilog HDL wrapper .v file. We didn't write the Verilog HDL for it, but we took a Verilog HDL wrapper for it, and it has made some Verilog HDL functionality for us. Hence it has inputs outputs like this. Now moving on to the inside cell structure. If you cut open the FPGA chip, and when you open the chip, if you can zoom in, this is the block RAM. Oh, I can't write, right? Oh, sorry. So this is the block RAM. You can see, right, how these block RAMs are connected internally with this set of lookup tables, multiplexers, demultiplexers, XORs, buffers, all these things. I mean, these are flip-flops. Architecture is like block RAMs can be connected to one of these elements, group of elements, group of circuits and elements, and this is how these are connected internally. And also to the DSP block, that is digital signal processing block, and in the exterior segments, these are also connected to the A to ADC controllers like analog to digital converters and all. With the ground output pins and input pins are also connected. These two have some architecture with Verilog VCC and ground are also to be connected for the functioning of the blocks. And then this is how it looks like, block RAM, and the internal structure is this. And I am showing it at IC stage. Inside the FPGA chip you can see the digital circuit looking like this, block RAM with set of inputs and outputs bus. Okay, now coming to the generating HDL wrapper, you can see from this block RAM, this thing, if you can open the Xilinx Vivado, you can see the generating HDL wrapper from it, from the sources file. It generates the Verilog HDL to you. But in the end of this session, I will try to give you an example of Verilog HDL file as well. And usually when you buy a FPGA, or when you get an FPGA from one vendor, let us say Spartan processor or RTX 7 FPGA architecture, if you get from a vendor, and from that vendor you will also get some packaging. In that packaging you will also find a user guide manual that can be found in online as well. In that user guide manual you can see what type of block RAMs you have in the FPGA. So every FPGA have these memory blocks which are BRAMs, and for that BRAM what can be the syntax of the Verilog HDL that you can write. So they will give a basic Verilog HDL example, and from that you can develop all these things such that you are designing your block RAM into your own design, um, like as per your own requirement for the project. If you want 64 by 64 memory, design it in that way, and if you want 4 kilobyte memory, design that into the 4 kilobyte memory. Okay, so coming to this, I hope you have seen the input clock, data in, data out, enable and reset, and write enable. Okay, you are writing it. Now come to the BRAMs. This is general theory, you need to understand and remember it. That is, BRAMs are used for storing lookup tables, for converting parameters, values, etc. Like these basic operations can be done with the BRAMs. Different lookup tables are predefined for various FPGAs. So how these lookup tables are predefined? Those are predefined by the vendors wherever you purchase the FPGA. For example, you are purchasing from Intel FPGA, Quartus Prime, Cyclone DE2 board or Cyclone DE4, DE5 board. You are getting the FPGA from the Intel vendor. So Intel vendor has some lookup tables for that particular FPGA. So every processor should have a lookup table. So inside this is the lookup table that can be connected to the block RAMs, and in the block RAM you can also store the lookup tables. So from where this lookup tables data is processed, from this BRAMs. So if I can write something, if this is a lookup table, this lookup table is connected to block RAM, and the data in the lookup table is sent through the lookup table, and in this architecture it is sent through the multiplexer and to the XORs or any other logic gates, and it is sent to the D flip-flop, and from the D flip-flop it is sent through the IO buffers. Somewhere in the IO buffers are available. So that is how the functionality works. Okay, now coming to the next thing, storing read-only data. Some BRAMs can also be made into the ROMs, read-only memories. Means constantly whatever the lookup table you have preloaded into it, from that you can load into the data out. General data, output pin. So general output pin. Okay. Creating FIFO to store cache or temporary data. Creating FIFO means, as we have known, FIFO is one kind of application at the IO buffer stage. That is one protocol. That one kind of hardware architecture or the realization of the hardware, where it pushes the data, or it transit the data from one input to the another input, like between two modules, between two peripherals, let us say, or between two elements which communicate with respect to the data. So it takes the data into one initial location as 00, and it takes out the data from it from the final location. So there is a first in first out of the data. So that is how it looks like. And then you can also have the rows of information, audios and videos. In the FIFO you can process the data in the cache memory, and crossing clock domains using FIFO. Like once you create FIFO from the block RAMs, you can also see crossing clock domains is CCD is one of the applications of FIFO, and mostly used for storing the data. Okay, and between two different clocks, the actual synchronization can be happening with the implementation of FIFO. That is nothing but crossing clock domains, and this FIFO can be implemented by BRAMs. Don't forget it. So because in the FIFO you can see there is a block RAM, RAM, which is another register or block. That register RAM, random access memory, that RAM is responsible for storing data in the registers. You can refer to the yesterday's session, and let's go to the BRAM structure. It has width and depth. It is usually like a normal memory, but in the FPGAs we represent in the BRAM. BRAM is a discrete component of an FPGA architecture, and there will be only limited number of BRAMs available on FPGA. So very limited number. If you can see, only this is one BRAM and this another BRAM. You have only 10 to 15 or 32 BRAMs, or depending on the package you buy, depending on the FPGA package that you purchase. Based on that package, that is why we have mentioned CSG 324 package in the initial days when we are developing the FPGA. So in that Xilinx Vivado, we have chosen the hardware with package of CSG 324. So that has some set of block RAMs, and if you go for CSG 325, it has some other set of BRAMs. So they are very limited. Keep in mind, and there are various types of configurations like single port configuration, dual port configuration, and FIFO configuration. Okay, these are different types of BRAMs that we can implement. But when it is a limited number, you should wisely use the BRAM. Are you using for only FIFO and you are leaving rest of them to be not processed in any other data transition? No, you should use them wisely. If you require only one FIFO, okay, turn one or two BRAMs into FIFO and use the other BRAMs in another application in your project. So you should use them wisely when they are limited. So how many are present, that can be known from the user guide manual. So every time when you purchase in hardware in electronics industry, either you will be getting a data sheet out of it for that device, for that element, for that sensor, or for that electronic component, or you will be given with a user guide manual. So how this works, how this device works, and what are the capabilities of this device, what are the specifications of that device, and under which circumstances you can utilize it, in which different types of applications you can utilize it. So these are all the things that you can notice from it. And there are different types of configurations, and some BRAMs can be used with single port configuration, only one single port, and some BRAMs can be used for dual port configuration, like both in and out. If single port only, only one input, only you can write, simple thing. And if you have both ports, you can read and write, you can read from it and you can write into it. Okay, always from the memory you can read, always to the memory you have to write. Okay, and then you can see most of the BRAMs can be initialized by the non-zero values. Usually in the initialization we will set clock as 0, reset as 0, and write enable as 0, read enable as 0. All these inputs, dn will be 0, all these will be 0, right? But these BRAMs can start at any point of the clock period, at any point of the input port. That is what initialization can be done with non-zero values means in terms of Verilog HDL while you are developing the architecture. So don't get surprised when the Verilog HDL wrapper generates the Verilog HDL code for this BRAM with some non-zero values initialization, like initialization like 6 bit hexa. You can start from, don't care, you can start from 3, some other value as an input. So you can give it to it and BRAM can work from that point. So there is no hard and fast rule for 0, starting initialization at 0. Okay, then single port BRAM configuration, how does it look like? What is the explanation of it? How does it look like? So for every time any RAM, you have port A and port B. Let us assume you have two ports at two ends. That is what I have designed here, a single port, and two ports means two sides. And let us consider for the single port configuration, in the single port configuration there will be no other clock, all the clocks are synchronous clocks. See, there will be only one clock. At one particular point of clock you can only write or you can only read. Particular clock, for example, if you are writing a clock like this, passage of the clock, for every passage of the clock you are writing. Let us see. And for every negage of the clock, here reading. Simple, na? How does it sound like? For single clock, for every transition, you need to look into it, whether it is writing data or reading data. So there is only one clock, which this clock can be utilized for write operation and read operation. Okay, then you all know these are the basic inputs. Clock A, write enable, address, write data, this is D in, and read data, this can be D out. Only the names will change. Here I have given with a good understandable names, but in the Verilog HDL in the previous designs we have used D in and D out. Okay, there is no hard and fast rule, as I have said, for the naming of the input ports and output ports, but usually what we can see is in the design you can see D in and D out. But what I have said here, I will say it now as write underscore data. What is wrong in it? To make you understand, I have made this. You can mention this in your Verilog HTML file as well, in the design file. No harm in it. But if you mention it, use it throughout the entire Verilog HTML code. That is my request. So in that kind of naming errors or syntax errors, don't make those mistakes, because you will never understand the error in the debugging window. So follow the rules, follow the syntax, write the Verilog HTMLs on your own. If you make mistakes, very good, make mistakes, realize those mistakes, don't repeat those mistakes. This is how you learn the programming, any programming, not only Verilog HTML. So coming to the inputs, this is single board configuration. What else we should know? The data can either be written or read with single clock signal. Okay, I have said this part already. So these are like key points to remember. That is why I have written these points every time in the everyday session. I write notes so that you will directly understand these are the important points. Hence, let us go to the dual port BRAM configuration. For the dual port BRAM configuration, we should keep in mind we have two different clocks which can be asynchronous, and we have write enable, and we have write enable from the port B as well at this point of clock, and we have read data and write data and address. So block RAM is utilized by the port A and B. For example, how this is connected, imagine now it is connected to a module here. Like this module can be ALU. Okay, this module can be ALU, but for this this entire thing is connected to a some source file as an input, where you are getting inputs from input.txt file. Okay, input.txt file. So this is connected to the module, where this is entirely connected to the data buffers, and the data from it is considered to this by using readmemh. That function is there, right? $readmemh. That from that you will take the data into the RAM, and now whatever data is taken from the RAM, from the input text file, that is sent through this read data. You never know, that is how it is used. So in this clock, read data, and that data is utilized in ALU for making some additions, subtractions, multiplications, divisions, and also logical and or what else we can see, right shift, left shift, and comparison, greater than, less than, and assigning, everything, every other ALU operation that it can do. You have also this XOR operation, XOR, XNOR, everything. Got it? XOR operation operator is this one. This is XOR operator. Got it? Not XOR, this is XNOR. So simple. In the dual port configuration, there are two ports with read and write. signals at different clock cycles, but we cannot read and write on the same point of the single clock cycle. For example, here you are writing it, then you need to read it. If you are writing from the port A, you can only read from the port B. I'll erase everything. Okay, don't get confused. So what it is saying is, at this point of clock cycle, if you are writing data into the memory, and then at that particular clock period of this port B, you can only read from it. So you can only read from it. Either only one task can be done, write and read from it, in the particular instance of two different clocks. Okay, but we cannot read and write on the same point of the single clock cycle. Never write data to the same address locations. I mean, what does this mean? Means you have a register here. Let us say the address location is 101. Okay, in that address location you have written data. What if you are collecting data from the port B, also writing data into the same address? What happens? The latest data sits, or it will throw an error by saying conflict of address. Conflict, that can be conflict. So never do those kind of mistakes if you are writing BRAM configurations. Usually you are not bothering about Verilog HDL for these BRAMs, whether it might be single port or dual port. Machine does the task. Like EDA, you have to generate the Verilog HDL for it, and in the larger complex designs, after you generate it, you need to verify it. Until you verify, there is no confirmation of using that Verilog HDL generated file into your design. So you need to simulate and verify it using test bench. So you have to write a test bench to check the BRAMs. So that is how you need test benches. But in exceptional cases, write and read operations can be done at the same cycle. If a clock cycle has this thing and another clock cycle has some slighter delay in this amount of time, remember, some slight delay of the transition of this thing. So if it is C1 and if it is C2, if at the same particular clock cycle, if these are both at the same frequency, same clock time period, but with some transition delay and fall delay, I mean rise delay and fall delay with the same a little bit, what it can see, at the first moment you can write and the second moment you can read. So simultaneously it happens, like from the same register you can write and you can read. Okay, from the same register with some miniature difference of the clock period. It is negligible, it is as same as the same clock, but at some rise delay, in the real time it is different, right? By the involvement of more the combinational circuits inside the entire complex design, there will be some delay introduced into your sequential elements. So that is the point to be taken. So hence the third configuration is FIFO BRAM configuration. That is, in the FIFO, never write to a full FIFO and never read from an empty FIFO. See, if this entire BRAM is a FIFO now, if you have a 0 values, what will you read? You can't read anything. That is what the meaning is. Never read from an empty FIFO. I would suggest you to understand this in your local language, whatever place you come from, but it will be very helpful if you realize this entire understandings and subject in your own terms, own languages. Then you can see this is a device that is operated between input and output, and you can also see how these changes are happening. So it is like telling this own explanation and telling this own subject knowledge to yourself with your own language, with your own convenience of understanding. See, why am I communicating in only English is. So it is a universal accepted way of communicating medium. But what my suggestion here is, to understand this entire training or entire understandings, try to analyze this part in your own explanations. Explain it to you yourself. Then you will get to know, okay, never write to a full FIFO. What does this mean? Okay, if it is the full FIFO, if it is full, see, the data is full, you have no data left, every register is full now, every register is full. What will you do? Can you write any more into the registers if there is no this thing? For example, as I have explained in the FIFO implementation, take a shelf and you have kept every book into the shelf and there is no space left there. Can you keep another book? No, you can't keep. But what if there is some space? Then you can keep another book. Likewise, you can't accommodate the writing the data. You can't accommodate the data by writing into the full FIFO, if it is full FIFO. And you can't read from an empty FIFO. What will you read if there is no data in it? So that is a major difference. So FIFO, what is happening? It is checking with whether the block RAM is full or block RAM is empty, to push the data from one location to another, or from one module to another module. So as I have said, this RAM is connected to the two modules, M1 and M2. So data from M1 goes to the FIFO. Now it is FIFO. Goes to the FIFO only if full is 0. It is not full, and empty is equal to 1. Understood? So then only you can write. For the read, it is reverse. Full should be 1 and empty should be 0 for read, and this is for write. So why am I repeating these things many times? To make you understand in a simpler terms. So whenever someone asks you, okay, can you design FIFO? Don't get panic. You understand the FIFO logic. You have already written Verilog HTML for the FIFO logics. Go refer to that video and then understand what all the blocks inside the Verilog HTML is doing. So we have two blocks, right? Initial block and always block. What is this initial block doing? Initial, begin, write enable is 0, and always block, write enable should be 1. Write enable should be 1. You can see for the initial begin block in the Verilog HTML of an FPGA chip, in the design, always understand what all these blocks are doing inside the Verilog HTML script. Hence, you will understand in a layman terms. Come to the other set of instructions or important points of the block RAM. Block RAM can be designed through different methodologies. What are the different methodologies? Till now we have seen the configurations. What are the different types of BRAMs we can make? From the block of BRAM, we can make single port BRAM, that it can only read and write at the synchronous clock, and also it can take dual port BRAM configuration such that it has two clocks at two different ports, and now you can read the data and write the data simultaneously, or you can only read and write from different locations of the registers inside the RAM at the stack of registers. So inside RAM you can see there are stack of registers which stores the data into the memory device. This is a memory device, random access memory. And going to the FIFO design, that is third configuration. FIFO design has first in and first out operations, where you can only write to the empty FIFO device, empty memory. If the memory is empty, you can write something into it, and if your memory is full, if memory is full, you can read, you can't write more. So it is the basic thing. And how will you implement it? What are different types of implementations or methodologies now? You have through instantiation, one thing, and another thing is inference. Third type of implementation is taking the interactive GUI. GUI is nothing but graphic user interface. Take the graphic user interface from an EDA vendor, whether you are using Altera Quartus Prime EDA tool or from the Intel, or you are using ARM based Xilinx Vivado EDA tool. Take these environments, EDA environments, and take a GUI and take the block RAM there and connect them manually. In this kind of thing, you can configure the BRAM. So these type of methodologies are, first one is instantiation by the automatic generated wrapper. In the initial days, we have took BRAM as an IP BRAM, and what we have done, we haven't written Verilog HDL for it, but the machine does for us. We have utilized the EDA tool from the Xilinx, and we have took the IP integrator and click the button of generating Verilog HDL wrapper. Then we have simulated a test bench and we have tested it by debugging the errors. That is how you have to check the Verilog HDL generated by the machine. Usually it doesn't make mistakes, but 99% of the time it is good. But for the 1%, it shouldn't ruin our hardware circuit. If your BRAM design is good and if you want to implement it on the FPGA, so if it has some errors and mistakes, and if the timing doesn't meet, or if the clock is not working properly, and if you are not getting the desired output, you can't load that error based design onto the FPGA. So that will be a bigger mistake. So to eradicate those errors, you need to make a test bench simulation like we have done, like BRAM_TB. And for that test bench Verilog HDL, we have given inputs and we have checked the Verilog HDL generated wrapper. And that is one way. Through inference means taking some other Verilog HDL resources from the neighboring module and using that in this Verilog HDL BRAM module. So it is mostly used when you are developing a bigger, larger Verilog HDL design. So for the complicated design with bunch of modules and elements, you can see you can refer this Verilog this block RAM from the neighboring design that is already existing. And third thing, as I have said, graphic user interface. So in the responsive availability of GUI in the EDA tools, but not suggestible for larger designs. Why? Because if it is a small implemented design of a memory for 1 kilobyte or 4 kilobyte of memory, okay, you can do. But what if you are designing an SRAM or some stable memory device which has a capacity of storing 128 GB? Basic, you are designing a memory for a mobile device or for some SSD like 512 GB SSD for your laptop. What if you are designing such kind of read-only memory device? You can't design that with a graphic user interface. That entire larger devices are designed through automation. How is this automation happens? So this automation happens through the set of commands given in TCL scripting, like TCL scripting language, or in the Perl scripting language. You should also know about these things, and these are very much asked in the VLSI based interview jobs, and you will get to know that in the next sessions as well. I will try to inculcate some of the interview questions as well. So let us go to the implementation of single block RAM, and that block RAM is nothing but module 64 by 64. In the earlier case, we have written mem 64 by 64. So this entire Verilog HDL structure that I am explaining now is given by the vendor itself. As I have said, for every packaging or for every FPGA chip that you acquire from a vendor, whether it might be Spartan, Artix, or whether it might be from Xilinx, or it might be from a Nvidia, or it might be from Intel, whatever FPGA chip or FPGA board that you acquire, it comes with an user guide manual, and in that user guide manual, with the limited BRAMs listed, there will be some specific BRAM Verilog HDL code, some basic sample Verilog HDL code that is written to declare the functionality of the BRAM. So this is how it is declared. This entire BRAM is declared. You have to mention input data in, address, write enable, clock, D out. All these inputs and outputs are declared in this manners, and you have to mention parameters. Layman understanding is nothing but address width will be 9 and data width will be 8, and these parameters are mentioned to use them universally in the neighboring Verilog HDL modules as well. So when you write address width as 9 in the entire bigger design, if you are using this BRAM of 64 by 64, you will never forget that, okay, what is the address size that I need to mention? It is 9. And what is the data width I should mention? How many data bits it should transfer? 8 bits of data, like 1 byte. So input, you need to mention address, and for the input another data in, you need to mention the size of the register, size of the wires. And input, write enable and clock are the signals, command signals. Write enable, at write enable you can write into the data. So it is a single port block RAM. So, and the outputs are declared. The first part is module declaration, second part is parameters and inputs, output. Third part is registers and wires. In the third part, registers and wires, you can see data out and memory declaration. When we are declaring memory, in either ways, memory is nothing but a matrix, two-dimensional matrix, which has width and depth of the bits of data stored in it. So this representation before the mem is nothing but width. So what this width represents? It represents how many number of bits you have. So how many number of bits you have? You have 8 bits of data. 1, 2, 3, 4, 5, 6 and 7, 8. So 8 bits of data. Done. But how many such type of 8 bits of data you should possess? You should possess address width. What is it? Another 8 bits. Okay. So now you have 8 registers. Each register is having 8 bits, and you have such 8 registers. You have 8 registers followed with 8 bits inside each register. That is how memory declaration is done. Then you will begin the process with always at the rate of passage. What are we doing here in the always block? We are writing. And also we are getting the data output into the D out from the memory address location. So we are also reading it. Whatever data you get from a memory, it is read process. Whatever data you write onto the registers, it is write process. So from the data input, you are writing into the memory address, and from the memory address you are writing into the D out, that is read process. So do remember these commands, these instructions. Once you get familiar with Verilog HDL structure and writing, right, without any hesitation, you will write it by yourself. So that is begin and end here. Don't make this kind of syntax errors and end the module. When you start it, end it. So this is the fourth thing you need to declare, always at the rate of passage, and this entire process is fifth step, and sixth step is nothing but end module you need to declare. So that is our today's thing, and most asked interview questions will be introduced from the next session. Stay tuned. And this is our FPGA. You can see whatever the architecture that we have discussed so far, these BRAMs are sitting here, and you can also design these kind of DRAMs and SRAMs. That's it for the today's session. Thank you, and if you have any questions, please let me know. I'll be here to answer everyone. Thank you guys.